In this illustration, we intend to simulate cantilever beam under a uniform pressure using solid, shell, and beam elements in the Abaqus software, and following that, compare the results gained with those obtained by using the exact solution method. As you observe in this picture, the length of the beam is 0.2 meters, its width is 0.02 meters, and its thickness is 0.002 meters. Here only elastic properties have been defined for the steel beam. The purpose of this analysis is calculating the deflection as well as the bending stress of the beam, which shall be done using solid, shell, and beam elements, and the results gained will be compared together. I will enter the Abaqus software for simulation. I will click on Create Part. I intend to create geometric shape of the beam. I will select the modeling space as 3-dimensional. From here, select Deformable, then Wire and Planar. Enter the rough size of the tracing page equal to 1 and continue. I will draw a horizontal line. And enter its length equal to 0.2 meters. Done. In the next step, I will enter Property module, click on Create Material. The beam is made of steel. I'll select Elasticity and Elastic from the Mechanical menu. Young modulus of steel is 207 gigapascal, and Poisson ratio is equal to 0.3 and OK. I will click on Create Section. From here, select Beam and the type of element beam as well. Continue. Click on Create Beam Profile. From here, select Rectangular and continue. As you observe in this picture, the width of the beam is 0.02 meters and its thickness is 0.002 meters. I will enter size of A equal to 0.02 meters and B equal to 0.002 meters. OK and OK. I will click on Assign Section, select Beam, Done and OK. Here we should distinguish the directions 1 and 2. To do so, I will click on Assign Beam Orientation, select Beam, Done. As you observe here, and direction 2 is towards y-axis. You can observe the beam in 3-dimensional form using Render Profile Beam option. In the next step, I will enter Assembly module, click on Create Instance and OK. I'll enter Step module, click on Create a Step. We will use one static general analysis in this question, that is in linear form. Here, since the question is a simple one and converging that is not so hard, we don't need to make any special changes in this box. So I'll click on OK. In the next step, I will enter load module. As it can be observed in this picture, we have utilized a fixed support at the left end of the beam. To create such a support, I will click on Create Boundary Condition. Here select Displacement Rotation and continue. I will select this point, done, and close all boundary conditions of displacement for it. I will click on Create Load. Here I intend to apply the linear load of 100 Newton per meter on the beam. So here I will select Line Load and continue. Select the beam, done, and enter negative 100 Newton per meter directed at y-axis. I will enter Mesh Module, click on Shade Part, enter Approximate Global Size equal to 1 millimeter and OK. I will click on Shade Part and yes, then I will click on Assign Element Type, select the beam, done. As you observe here, the element family has been put on beam and the element's name is B31, which can be observed here. I will enter Job module, click on Create Job. Continue, OK, and click on Submit. Well, as you observe, since the question was so easy, it was solved so quickly. Well, I will click on Result. Here, I click on Allowable Multiple Plot State and then click on Plot Undeformed Shape. In this manner, you can observe the deformed and undeformed models simultaneously. Here, we intend to compare the results gained from Abaqus software with those gained from the exact solution. First, we will solve the question using the exact solution method, and in the next step, compare those results gained from exact solution method with those obtained from the Abaqus software. In this picture, you can observe the deflection at the free end of cantilever beam under uniform load. You can also find its related formula here as well, in which Q stands for the uniform load, the unit of which is Newton per unit length. L here stands for the length of beam, E stands for Young modulus, and I stands for area moment of inertia of cross section. In this question, Q is equal to 100 Newton per meter. The length of beam is equal to 0.2 meters. Young modulus is equal to 207 gigapascal, and inertia moment has already been calculated here. Deflection at the free end of the beam, or the same vertical displacement at the free end of the beam, is equal to 7.240 147 millimeters that has been got from the exact solution. Now we intend to calculate the vertical displacement at the free end of the beam using the Abaqus software. So I will select U from here, then U2. As it can be observed here, the vertical displacement at the free end of the beam is equal to 7.247 millimeters. That has been distinguished with blue color. As you observe here, the results gained from the exact solution and those obtained from the Abaqus software are very conforming and have the same outcomes. In this Excel file, we intend to compare the results gained from the Abaqus software with those obtained from the exact solution in order to calculate the difference between them. In this column, you observe the deflection at the free end of the beam using the exact solution and the quantity of which is equal to 7.247 millimeters. The reflection at the free end of the beam using the Abaqus software is equal to 7.247 millimeters as well, in which the error is equal to 0. Actually, the results gained from the Abaqus software are exactly the same as those obtained by exact solution method. The next issue we intend to obtain is the bending stress. You can use this formula for calculating the bending stress, in which M stands for moment, I stands for inertia moment, and Y is the perpendicular distance from neutral axis. And you can study its related explanations on this page. Here the formula for bending stress has been given, in which sigma is actually bending stress, and you can calculate that based on this relation. Here we will use this formula in order to convert the line load to the concentrated force, and here the concentrated force is equal to 20 Newton. The bending stress having been gained using the exact solution method at the fixed support is equal to 150 megapascal, and you can observe these quantities in this column. Now we intend to calculate the bending stress using the Abaqus software. So here I'll select stress parameter, and here select the longitudinal stress. The longitudinal stress at the fixed support is equal to 149.3 megapascal. Here I will enter the longitudinal stress having been obtained from the Abaqus software, equal to 149.3 megapascal. Now we intend to calculate the error occurred between the exact solution and the Abaqus software. To do so, we would only need to subtract the amount 149.3 from 150, then divide the result obtained by 150, and finally multiply that by 100. The scale of error is equal to 0.46%. In the next step, we intend to calculate the effect of mesh on results, or in other words, mesh sensitivity. To do so, we should minimize mesh's size, so I will enter the size of mesh is equal to 0.5 millimeters and click on mesh part. I will click on create. Continue, OK, and click on submit. Here we have downsized meshes and would like to see what effect they will have on the outcomes. I will click on result. First, we intend to calculate the deflection at the free end of the beam, the quantity of which is equal to 7.247 millimeters. Then we will calculate the longitudinal stress using the Abaqus software, and its quantity is equal to 149.6 megapascal. As you observe, no changes was made in the quantity of deflection when we downsized the meshes, but the quantity of longitudinal stress slightly approached the results gained by the exact solution method. We will calculate the difference between the results gained by the exact solution method with those obtained in the Abaqus software. The scale of error is equal to 0.26%. Well, this question was finally solved using the elements of beam, and here you observe the results gained from the Abaqus software, which you can compare them with those obtained by the exact solution method, and you observe the scale of its error. In the next step, we intend to solve this question using the shell elements. I will click on Model menu, then Copy Model. I will name this model Shell Elements, and OK. Here I will click on Create Part. I intend to create the beam part. I'll select the modeling space as three-dimensional. From here, deformable, then shell and planar, and continue. I'll draw a rectangle. The length of beam is 0.2 meters. Its width is 0.02 meters. And click on Done. In the next step, I will enter Property module. Click on Assign section. Select the beam. Done. Here I click on Create section. Here select Shell and Homogeneous. Continue. As you observe in this picture, the thickness of the beam is 0.002 meters. OK and OK. Here you can observe the thickness of the beam using the render shell thickness option. In the next step, I'll enter assembly module. Here, I'll remove the beam we had created in the previous step. Click on Create Instance and enter the new part into the assembly module. I will enter Step module. Here, we don't need to make any special changes, so I'll enter Load module. Here, remove this boundary condition, click on Create, select Displacement Rotation, and continue. I will select this edge, done, and close all boundaries of displacement for it. In the next step, I'll remove the line load which had been created in the previous step. Then click on Create. Here, select Pressure and continue. I will select the beam, done. Select the top surface that is in brown. Here you can convert the line load to pressure load using this relation. The amount of pressure is equal to 5000 Pascal, and then I will click on OK. In the next step, I will enter Mesh module. Click on Seed part, enter the sizes of elements equal to 0.001 meters, just as the previous example. Click on Mesh part and yes. Then I will click on Assign Element Type, select the beam, done. As you observe, the element family is on shell and its name is S4R, which can be observed here. I will enter Job module. Continue, OK, and click on Submit. As you observe, the analysis was done so quickly, so I will click on Result. Here you can observe the results having been obtained from analysis. As we mentioned, as for the previous model, we intend to calculate the vertical displacement at the free end of the beam using the Abaqus software. I will select U3. Here deflection is equal to 7.162 millimeters, so I'll enter the quantity in the Excel software. As you observe, there is a very slight difference between the results gained from the Abaqus software with those obtained by the exact solution method. Now we will calculate this difference here. Well, the scale of error was calculated, the quantity of which is equal to 1.17%. In the next step, we intend to calculate the quantity of the longitudinal stress. The quantity of longitudinal stress which had been obtained from the Abaqus software is equal to 174 megapascal. Now we intend to calculate the scale of difference between the stress resulted from the Abaqus software with that obtained by the exact solution method. Here, the scale of error is equal to 16%. As you observe, here the difference between the Abaqus software and the exact solution is very little, but in the longitudinal stress there is a rather considerable difference. Now here we will downsize the meshes and you can observe its effects on the results which will be gained. To do so, I will click on Seed Part, enter the approximate global size equal to 0.5 millimeters. I will enter Job module, click on Create. Continue, OK, and click on Submit. The analysis was done successfully, so I'll click on Result. First, we will calculate the deflection at the free end of the beam, the quantity of which is equal to 7.162 millimeters. Here the scale of error is equal to 1.17%. As you observe, no change was made in the results gained in deflection when we downsized the meshes. Now we will survey the results obtained from the longitudinal stress. Here the quantity of longitudinal stress is equal to 176.3 megapascal. The scale of error will be 17.53%. Here, the results obtained from the Abaqus software using the shell elements were compared with those gained by the exact solution method. In the next step, I will enter the Abaqus software and intend to solve the problem using the solid elements. I will click on Model, then on Copy Model, name this model Solid Elements, and OK. I will click on Create Part. Here, select 3D, Deformable, Solid, and Extrusion, and Continue. I will draw a rectangle. Enter its length equal to 0.02 meters, its width equal to 0.002 meters. Click on Done and enter the length of the beam equal to 0.2 meters in this manner. I will enter Property module, click on Create Section. Here, select Solid, Homogeneous, and Continue, and OK. I will click on Assign Section, select the beam, Done. Here, select Solid Elements, and OK. I will enter Assembly module. Here, I'll remove the beam which had been entered into the assembly module in the previous step and enter the new part instead of that. I will enter Step module. Here we don't need to make any special changes, so I'll enter Load module. Remove the boundary condition which had been created in the previous step and click on Create, select Displacement, Rotation, Continue, select this edge, Done, and close all boundary conditions of displacement for it. I will also remove the load which had been created in the previous step. Click on Create again. Here select Pressure, Continue, select this surface, Done. Enter the pressure equal to 5000 Pascal and OK. I will enter Mesh module. Here I'll first click on Seed part, enter the sizes of elements equal to 0.001 meters. Click on Mesh part and Yes. I will click on Assign Element Type, select the beam, Done. Here the element family is on 3D Stress and the name of the elements is C3D8R. I will enter Job module, click on Create. Continue, OK, and click on Submit. Well, the analysis was done successfully, so I'll click on Result. Just as the same we did in the previous step, we'll first calculate deflection. The quantity of deflection in the Abaqus software is 9.5 millimeters, and as you observe, there is a considerable difference between that with the quantity we had in the exact solution. The scale of error here is equal to 31%. Actually, if we use 1 millimeter elements, The difference between the Abaqus software and the exact solution would be 31%. The next case which should be surveyed is the longitudinal stress. Here I'll select S33. The quantity of longitudinal stress in fixed support using solid elements is equal to 115.8 megapascal. As you observe, here there is a considerable difference between the results gained from the Abaqus software with those obtained by the exact solution method. Here the scale of error is equal to 22.8%. Here I'll downsize the meshes and survey its effects on the results. To do so, I will click on seed part, enter approximate global size equal to 0.5 millimeters, and click on mesh part. As you observe, 64 elements will be put on this. I will enter job module, click on create. Continue, OK, and click on submit. The analysis was done successfully, so I'll click on result. Here, deflection is equal to 7.63 millimeters. As you observe, the results of the Abaqus software will approach those gained by the exact solution when we downsize the meshes, and the results will look to be real indeed. Now, here we will calculate the scale of error from the Abaqus software and that of the exact solution for the solid elements. As much as the scale of error is equal to 5.28%, you observe we downsize the elements as the same, and in this way the scale of error will decrease. Here we will calculate the longitudinal stress using the Abaqus software, the quantity of which is equal to 142 megapascal. As it can be observed, here also the results of the longitudinal stress will get closer to those obtained by the exact solution method as we downsize the meshes more. Well, the scale of error is equal to 5.26%. Well, here this table was completed, and you can compare the results gained from the Abaqus software with those obtained from the exact solution. It can be observed in this table that we have solved the question in three different states. First, using the beam elements, and in the step after that, we did so using the shell elements, and finally by using solid elements, and the results of which were compared together. As you observe, the results gained from the beam elements are very exact and so close to those obtained by the exact solution method. If you use finer meshes in solid elements, you will be able to obtain the exact results as well, but if you don't use such meshes, your results will be far cry from those gained by the exact solution method. In this part, we intend to discuss the beam, shell, and solid elements. The discussion revolves around the issue when we can use shell elements. If the length and width to thickness ratio is more than 10, we can use shell elements. Of course, it's a suggestion only, and there is no necessity in it. But since there was such a condition in this question, we were able to use shell elements. Here it is asked again when we can use beam elements. If the length to width and thickness ratio is more than 10, we can use beam elements, and it's a suggestion only, and there is no necessity in it. Since there was such a condition in this present question, we were able to utilize beam elements. You can even solve this problem using solid elements. Of course, you should note that if you want to simulate the beam using solid elements, you should use fine meshes in order to get proper results. In general, we can say that you can solve this problem using all these shell, beam, and solid elements and get good results.